Sequences Part 2. Precise definition of the limit of a sequence. A sequence A sub n converges to a limit L if, given any positive number epsilon, no matter how small, there is a positive integer capital N such that A sub n is between L minus epsilon and L plus epsilon for all little n greater than or equal to big N. In other words, the terms of the sequence eventually become and remain within epsilon of L no matter how small epsilon is. Now let's look at a picture to see how this works. Here we have the graph of a sequence which apparently has a limit of 1. Think of a small open interval centered at 1 on the y-axis extending from 1 minus epsilon to 1 plus epsilon. That interval corresponds to a narrow band about the line y equals 1. Our definition of limit says that points on the graph eventually enter and remain inside of that band. Notice that this happens when n is greater than or equal to capital N, where capital N is roughly 60 here. Now, if epsilon were smaller, we would simply have a narrower band centered on the line y equals 1, and the points on the graph eventually enter and remain inside of that band, this time when little n is greater than or equal to capital N equal to roughly 130. The point is that no matter how small epsilon is, that is, no matter how narrow this band is, we can always find such a capital N. One final remark before we leave this page. Notice that the condition A sub n between L minus epsilon and L plus epsilon simply says that A sub n is within epsilon of L, so that inequality can be restated as follows. The absolute value of A sub n minus L is less than epsilon. And let's look at an example to illustrate how we can use the definition of the limit to prove a specific limit. Let's show that the limit as n goes to infinity of n plus minus 1 to the n over 4n minus 3 is equal to 1/4. We begin by letting epsilon be an arbitrary positive number. We need to find capital N so that the absolute value of n plus minus 1 to the n over 4n minus 3 minus 1/4 is less than epsilon when little n is greater than or equal to capital N. In other words, we need to answer the question, how large must n be in order that the absolute value of the nth term of the sequence minus 1/4 is less than epsilon. Our next step is to simplify and then estimate the absolute value of n plus minus 1 to the n over 4n minus 3 minus 1/4. We do this by combining the two terms over a common denominator, 4 times 4n minus 3. Simplification shows that the numerator equals the absolute value of 4 times minus 1 to the n plus 3. So the numerator there only takes on two different values. It equals absolute value of minus 1 when n is odd, and equals the absolute value of 7 when n is even. So it's always less than or equal to 7, and so the entire quotient there is less than or equal to 7 divided by 4 times 4n minus 3. Therefore, the absolute value of the difference between the nth term of the sequence and 1/4 will be less than epsilon if 7 over 4 times 4n minus 3 is less than epsilon, and by multiplying by 4n minus 3 and dividing by epsilon, we see that this is true if 4n minus 3 is greater than 7 over 4 epsilon. That is, 4n greater than 7 over 4 epsilon plus 3. And by dividing by 4, we see that that is true when n is greater than 7 over 16 epsilon plus 3/4. So we're essentially done. The number capital N can be taken to be any integer greater than or equal to 7 over 16 epsilon plus 3/4. Notice that the smaller epsilon is, the larger that number will be. Boundedness. A sequence A sub n is said to be bounded if there are numbers little m and big M such that A sub n is between little m and big M for all n. Here the number little m is often referred to as a lower bound for the sequence, and the number capital M is called an upper bound for the sequence. So the sequence is bounded if it has both a lower bound and an upper bound. A few examples. The sequence n divided by n plus 1, as n goes from 1 to infinity, is bounded because n over n plus 1 is greater than or equal to 0, and it's also less than or equal to 1 for all n. So 0 is a lower bound and 1 is an upper bound. The sequence 1 over 2 plus minus 1 to the n is bounded, since clearly every term is greater than or equal to 0, as well as less than or equal to 1. So 0 is a lower bound, and 1 is an upper bound. But let's notice that we could also get a greater lower bound here. The terms of the sequence are always either 1/3, which happens when n is even, or 1, which happens when n is odd. So 1/3 is also a lower bound, and it is in fact the greatest of all the lower bounds. The sequence 1, 1/2, 3, 1/4, 5, 1/6, and so on is not bounded. Notice that the sequence has a lower bound. In fact, every term is greater than or equal to 0, but it has no upper bound. The sequence minus 1 to the n times n is not bounded. Notice the terms here are minus 1, 2, minus 3, 4, minus 5, 6, and so on. And so this sequence has neither a lower bound nor an upper bound. Another important attribute of certain sequences is monotonicity. A sequence a sub n is said to be decreasing if a sub n plus 1 is less than a sub n for all n. In other words, every successive term is less than the previous one. The sequence is said to be increasing if a sub n plus 1 is greater than a sub n for all n. In other words, every successive term is greater than the previous one. The sequence is non-increasing if a sub n plus 1 is less than or equal to a sub n for all n. And the sequence is said to be non-decreasing if a sub n plus 1 is greater than or equal to a sub n for all n. We remark here that this terminology is not universal. Some authors use the term decreasing when a sub n plus 1 is less than or equal to a sub n for all n, increasing when a sub n plus 1 is greater than or equal to a sub n, and then use the term strictly decreasing when a sub n plus 1 is less than a sub n for all n, and strictly increasing when a sub n plus 1 is greater than a sub n for all n. So it's important to be aware of the agreed upon terminology with which you're working. Now let's also note that according to our definitions, any sequence that is decreasing is automatically non-increasing, and any sequence that is increasing is automatically non-decreasing. Now, a sequence a sub n is said to be monotonic if it is either non-decreasing or non-increasing. A few examples. The sequence 1/2, 2/3, 3/4, 4/5, and so on, which is the sequence n over n plus 1, as n goes from 1 to infinity, is clearly an increasing sequence, since each term is greater than the one before it. The sequence 1, 1/2, 1/3, 1/4, 1/5, and so on, which is the sequence 1 over n, as n goes from 1 to infinity, is decreasing. And the sequence 2, 2, 1, 1, 1/2, 1/2, 1/4, 1/4, 1/8, 1/8, and so on, is non-increasing since each successive term is less than or equal to the preceding term. And finally, we note that all three of these sequences are monotonic. A sequence a sub n is said to be eventually monotonic if the sequence a sub n, as n goes from capital N to infinity, is monotonic for some n. In other words, all of the terms of the sequence, starting with the capital Nth one, satisfy the definition of being non-increasing or non-decreasing. Likewise, the sequence is eventually decreasing, increasing, non-decreasing, or non-increasing if the sequence beginning with little n equals capital N has that property for some capital N. Example: show that the sequence n over n squared plus 100 as n goes from 1 to infinity is eventually decreasing. A common approach when trying to show that the terms of a sequence are monotonic is to look at the difference between a sub n plus 1 and a sub n. Here, a sub n plus 1 minus a sub n is equal to n plus 1 over n plus 1 squared plus 100 minus n over n squared plus 100. Now, when we combine those terms over a common denominator, the numerator is 100 minus n squared. Since the denominator here is always positive, and since the numerator is a quadratic expression in n with a negative leading coefficient, we can conclude that a sub n plus 1 minus a sub n is negative when n is greater than the positive 0 of 100 minus n squared, which turns out to be about 9.5. Consequently, a n plus 1 is less than a sub n when n is greater than or equal to 10. Thus, the sequence is eventually decreasing. Now let's look at an alternative method for showing the same thing. Let f of x equal x over x squared plus 100, and notice that the nth term of the sequence is simply f of n. Using the quotient rule, we find out that f prime of x is equal to a fraction with denominator x squared plus 100 squared, and numerator equal to 1 times x squared plus 100 minus x times the derivative of the denominator, which is 2x. This simplifies to 100 minus x squared divided by x squared plus 100 quantity squared, which is less than 0 when x is greater than 10. Therefore, f of x is decreasing for all x greater than or equal to 10, and so f of n plus 1 is less than f of n when n is greater than or equal to 10. In other words, a sub n plus 1 is less than a sub n when n is greater than or equal to 10, and so the sequence is eventually decreasing. Example: show that the sequence minus 1 to the n divided by n as n goes from 1 to infinity is a, bounded, and b, neither monotonic nor eventually monotonic. Obviously, minus 1 to the n divided by n is greater than or equal to minus 1 and less than or equal to plus 1 for all n greater than or equal to 1, so the sequence is bounded. Now, if n is odd, notice that minus 1 to the n plus 1 over n plus 1 is a positive number, while minus 1 to the n divided by n is a negative number, and so consequently the n plus first term is greater than the nth term if n is odd. On the other hand, if n is even, then the n plus first term is negative, while the nth term is positive, and so the n plus first term is less than the nth term. So there is no index capital N at which the sequence becomes either increasing or decreasing. In fact, any sequence whose terms alternate in sign is neither monotonic nor eventually monotonic. Now that we're familiar with the concepts of boundedness and monotonicity, we can state a very important theorem. If the sequence a sub n converges, then it is bounded. If the sequence a sub n is bounded and eventually monotonic, then it converges. In particular, if the sequence is bounded and non-decreasing for n greater than or equal to capital N, the limit is the least number L satisfying a sub n less than or equal to L for all n greater than or equal to capital N. Here's the graph of a bounded increasing sequence. The limit is the least number that's greater than or equal to every term of the sequence. We call this number the least upper bound of the sequence. So a bounded non-decreasing sequence converges to its least upper bound. Here's the graph of a sequence that is eventually non-decreasing. The limit is not an upper bound of the sequence necessarily, but it is the least upper bound of the part of the sequence that is non-decreasing. On the other hand, if the sequence is bounded and non-increasing for n greater than or equal to capital N, the limit is the greatest number L satisfying a sub n greater than or equal to L for all n greater than or equal to capital N. Here's the graph of a bounded decreasing sequence. Its limit is the greatest lower bound of the sequence. For a sequence that is eventually non-increasing, the limit is not necessarily the greatest lower bound of the sequence, but it is the greatest lower bound of the part of the sequence that is non-increasing. Recursively generated sequences. Given a function g, we can define a sequence a sub n as n goes from 0 to infinity as follows. Let a naught be given, and let a sub n equal g of a sub n minus 1 for n equal to 1, 2, 3, and so on. In other words, each successive term in the sequence is computed from the previous term using the function g. The computation of such a sequence is sometimes called iteration with the function g. Example: let a sub 0 equal 1, and let a sub n equal 1 over 1 plus a sub n minus 1 for n equal to 1, 2, 3, and so on. The first few terms of the sequence are a0 equals 1, A1 equals 1 over 1 plus 1, or 1/2. A2 equals 1 over 1 plus 1/2 equals 1 over 3/2, or 2/3. Then A3 equals 1 over 1 plus 2/3, which equals 3/5. A4 equals 1 over 1 plus 3/5, which equals 5/8. A5 equals 1 over 1 plus 5/8, which equals 8/13, and so on. Here are the terms of the sequence in decimal form. Notice that the sequence appears to be approaching a limit somewhere near 0.62. A theorem. If the sequence generated by a sub n equals g of a sub n minus 1 converges to L, and if g is continuous, then L satisfies the equation g of L equals L. In other words, L is what is often called a fixed point of the function g. Example, let a0 equal 1 and a sub n equal 1 over 1 plus a sub n minus 1 for n equals 1, 2, 3, and so on, as in the previous example. Assuming that the sequence converges to a number L, the theorem tells us that L satisfies the equation 1 over 1 plus L equals L. So we can solve for L. We multiply both sides of the equation by 1 plus L to obtain 1 equals L plus L squared. Then we rearrange this quadratic equation, writing it as L squared plus L minus 1 equals 0. And now the quadratic formula, along with the fact that the limit is going to be a positive number, tells us that L equals minus 1 plus the square root of 5 divided by 2. This is the exact value of the limit of the sequence. Web plots. A web plot is a device for visualizing this type of recursive sequence. Let's look at the same sequence as the one in the previous two examples. It's generated by the formula a sub n equals 1 over 1 plus a sub n minus 1. The function involved here is g of x equal to 1 over 1 plus x. So we begin by sketching the graph of y equals g of x near the starting point a naught equal to 1. Then we add to the picture the graph of y equals x. The previous theorem tells us that if the sequence converges to a limit, that limit satisfies the equation g of x equals x, and so the limit will be the x-coordinate of the point of intersection of these two graphs. Now to draw the web plot, we begin by locating a sub 0 on the x-axis. Then we go up to the line y equals x, which tells us where a sub 0 is on the y-axis. Next we draw a line from the line y equals x down to the graph of y equals g of x. The y-coordinate there is g of a naught, which is a1. Next we draw a horizontal segment from that point on the graph of g over to the line y equals x. That shows us where a1 is on the x-axis. Next we draw a vertical segment up to the graph of g again, which tells us where a2 is on the y-axis. And now by drawing a horizontal segment over to the line y equals x, we locate a2 on the x-axis. Then we draw a vertical segment down to the graph of g, followed by a horizontal segment over to the graph of y equals x. That shows us where a3 is on the x-axis. Now we continue this process, drawing vertical segments to the graph of g, followed by horizontal segments over to the graph of y equals x, and it becomes clear that we're constructing a path that is spiraling around the point of intersection of these two graphs in a sense, and getting closer and closer to that point of intersection. Here's the ordinary graph of the first 10 terms of this sequence. The spiral nature of the web plot corresponds exactly to the zigzag nature of the ordinary plot. Now let's sketch a few more web plots for sequences generated by a sub n equal to g of a sub n minus 1 for a generic function g. First, let's suppose that g has a graph as indicated in this picture here. Notice that near the point of intersection, the slope of the graph of g is positive and less than 1. Now suppose that the sequence begins with this a naught on the x-axis. We go up to the line y equals x and then draw a vertical segment up to the graph of g. That locates a1 on the y-axis. Now a horizontal segment over to the graph of y equals x locates a1 on the x-axis. A vertical segment up to the graph of g locates a2 on the y-axis, and then a horizontal segment over to the graph of y equals x locates a2 on the x-axis. We continue this process of moving vertically to the graph of g and then horizontally to the graph of y equals x, and we see that the plot bounces back and forth between these two graphs and gets closer and closer to the point of intersection. Also notice that this web plot indicates that the sequence is an increasing sequence and that it is bounded, because the web plot can never escape that region between the two curves. And so we can conclude that the sequence does indeed converge to a limit L that's equal to the x-coordinate of the point of intersection of the two graphs. Now suppose that we started with an A0 that's to the right of the point of intersection of the graphs. Then we'd begin the web plot by drawing a vertical segment from the line y equals x down to the graph of g, then moving over to the graph of y equals x, and then down to the graph of g again, and so on, and it becomes clear that with this value of A0, the sequence also converges monotonically to that same limit. Now suppose that the graph of g looks as it does here. Notice that at the point of intersection we have a relatively small negative slope. Now let's suppose that we begin our sequence with this value of A0, so we start the web plot by drawing the vertical line from the line y equals x up to the graph of g above this A0. Then we move horizontally to the graph of y equals x, and then vertically to the graph of g, horizontally to the graph of y equals x, then vertically to the graph of g, and so on. And it becomes clear that this web plot is spiraling in toward our point of intersection, just like in the example on the previous page. So this sequence is not monotonic, but nonetheless convergent. And we would see similar behavior for other values of A0 nearby. Now suppose that the graph of g looks like this. Notice that near the point of intersection, the slope of the graph of g is greater than 1. Now suppose we begin with an A0 that's fairly close to the x-coordinate of the point of intersection. We begin the web plot by drawing a segment from the line y equals x to the graph of g, followed by a horizontal segment from the graph of g over to the line y equals x, and so on. Notice that the sequence is actually moving away from the x-coordinate of the point of intersection on the graph. In fact, the sequence here appears to be converging to 0, which is the x-coordinate of a different point of intersection of the two graphs. If that point of intersection were not there, the sequence would simply diverge. Also, notice that if A0 is to the right of the x-coordinate of the point of intersection, then the web plot moves away from that point of intersection, and it appears that the sequence will diverge, evidently increasing toward plus infinity. Finally, notice that we would see the same type behavior no matter how close A0 is to the x-coordinate of this point of intersection. Now let's suppose that the graph of g looks like this. Notice that nearby the point of intersection, the graph of g has a slope that's less than -1. Now again, suppose that we start with an A0 that is close to the x-coordinate of that point of intersection. We begin the web plot by drawing a vertical segment from the line y equals x up to the graph of g, followed by a horizontal segment over to the graph of y equals x, followed by a vertical segment down to the graph of g, and so on, and it becomes evident that the sequence is moving away from the x-coordinate of this point of intersection, and doing so in a manner that is not monotonic. In fact, the web plot is spiraling out away from that point of intersection. These four plots illustrate typical behavior of such sequences near a fixed point. In the first picture, g' of x is between 0 and 1 for x near the fixed point. As a result, the sequence converges monotonically to the fixed point, provided that A0 is sufficiently close. In the second picture, g' is between -1 and 0. Consequently, the sequence converges to the fixed point if A0 is sufficiently close, but the sequence is not monotonic. In fact, we could refer to this type of convergence as alternating convergence, since the terms of the sequence jump back and forth across the limit L. In the third picture, g' of x is greater than 1 near the fixed point, and as a result, no matter how close A0 is to the fixed point, the sequence always moves away from that fixed point and typically diverges or else converges to some other fixed point. And in the fourth picture, g' of x is less than -1 near the fixed point, and as a result, the web plot spirals out away from the fixed point, and so the sequence either diverges or else converges to some other fixed point. Example. The number square root of 3 plus square root of 3 plus square root of 3 plus square root of 3 and so forth is interpreted to mean the limit of the sequence whose terms are square root of 3, square root of 3 plus square root of 3, square root of 3 plus the square root of 3 plus the square root of 3, and so on. Notice that each term here, starting with the second one, is equal to the square root of 3 plus the previous term. In fact, we can describe the sequence as follows: a naught equal to 0, and a sub n equal to the square root of 3 plus a sub n minus 1 for n equal to 1, 2, 3, and so on. Here we've appended 0 to the beginning of the sequence, but that will not have any effect on its limit. Let's sketch the web plot to show that the sequence is bounded and increasing and therefore convergent, and find the exact limit of the sequence. To sketch the web plot, we need the graph of the function g of x equal to the square root of 3 plus x, as well as the line y equals x. Since every term in the sequence will be greater than or equal to 0, we really only need the first quadrant portion of this picture. So we begin with a naught equal to 0 and draw a vertical line up to the graph of g, followed by a horizontal line over to the line y equals x, then up to the graph of g and over to the graph of y equals x, and so on. So it's clear that this is an increasing sequence, and it's also clear that the sequence is bounded, since the web plot can never get out of that region between the two graphs. So, since the sequence is monotonic and bounded, we're guaranteed that it has a limit, and we also know that its limit will satisfy the equation square root of 3 plus L equals L. To solve that equation, let's square both sides and rearrange, and we have 0 equals L squared minus L minus 3. And now the quadratic formula, together with the fact that the limit will be positive, gives us L equal to 1 plus the square root of 13 divided by 2.